Okay, so now we've looked at a shunt field connected DC motor, and we've also looked at a series field DC motor. We've seen different characteristic curves for both of those motors, certain advantages to using one over the other. And I guess if you want to summarize it in one statement, you might say that the shunt field maintains a more constant speed over a load range, and a series field provides a higher starting torque. So what if we could combine those two features of a series field and a shunt field in one machine and benefit from the characteristics of both? That would be great, and that machine is called a compound motor, or sometimes we'll hear it referred to as a cumulative compound motor. So this shows us a connection diagram of a DC compound motor, and also shows us a schematic diagram of a DC compound motor. What I'll point out first here on this is that, of course, this would be showing us the series connection, right, where we're running all the current through the field that runs through the armature. And even our textbook goes to the trouble to show that as a larger gauge wire. And then here, over here, shows the shunt field that is incorporated into the connection. Again, you know, what we're seeing here is this is termed excitation current. And this is, you know, it's just the current that is in the motor. And it, you know, it is the same. And because of that, it is labeled as just I. Now, if we look at something I think, you know, is a little easier to see, would be this schematic representation of that. Here we, of course, can clearly see how the shunt field is connected in parallel with the armature. All right, so out here is where we would hang a load. You know, this is where we'd connect the load out here. And then at the same time, what you see here is parallel connection, but also this series connection. And so all the current is running through the series field. He goes on to say that the shunt field is always stronger than the series field. That sounds like a good true-false question. And he also says that when the motor runs at no load, the armature current is very low. Okay, so we have no load out here. This armature current tends to be very low. And so the series field magnetomotive force is going to be very small. But at the same time, the shunt field is fully excited because it's in parallel. And so the motor behaves like a shunt machine, and it won't tend to run away at no load, the advantage of that field. So as the load increases, the magnetomotive force of the series field is going to increase. And as this MMF increases, the total is going to increase, right? It's all cumulative. And so what we get is with the increasing load, the speed is going to fall, because we know that that flux per pole, you know, sits down there in the denominator. And if this goes up, speed is going to go down, that inverse relationship across there. Motor speed with a compound generator falls with increasing load at a range from no load to full load from about 10% to 30% across a range of loads. Okay, so that's primarily the idea behind a compound motor. And I will point out this too. These are the actual connection labels that we see in the lab. And when I go through here and we do the DC Motors lab, we'll see we're actually using those connection designations to complete our circuits. So this is realistic as it shows. One thing he mentions on page 107, not sure how important it is, but he talks about something called a differential compound motor. And what it involves is that the way that the series field is wound opposes the shunt field. So you actually get an increase in speed as the load increases. Okay. You know, I don't know really why he goes into really mentioning that. And the only reason I'm mentioning it is because that appears in this very nice graph, figure 513. Here, you know, one of the devices grafted is this differential compound, and as you can see, it's the only one where the speed is increasing as the torque increases. But he goes on to say that, you know, there's no real common applications for this. But what I want you to primarily pay attention to is the shunt, series, and compound. And notice how the shunt is the flattest. And now we're graphing torque on the x-axis and speed on the y. So this indicates a not large change in speed across a change in torque. Okay, so it's flatter than the other curves, in other words. All right, so we see that, and then I'm going to jump up to the series. And the series, we said, had this characteristic of high starting torque. And what we see here is, if we look at from the two extremes on the series, we're seeing a large change in speed, right, across that torque range. So it has the most variation in speed. And then what we see in the middle, and this is the benefit of this compound motor, and I'll try to see if I can follow it through here. Yeah, it is here. And then, why don't I try to do this? Shunt is here. And then series would be here. Okay, so add a little color to that, maybe that helps us see those two things. And across the range there, you know, we can see where the compound sits in between the series and the shunt motor, between the two conditions that are stated there. Okay, figure 514 shows a hot strip finishing mill. I don't know exactly what the relevance of that is. It's just a picture, and it looks like one of those places that we probably wouldn't want to work. And it looks like it's really an old picture, doesn't it? It says it's a General Electric facility showing a 2,500 kilowatt DC motor. Interesting operation there. But anyway, so that's section 511.